Hello and welcome to our journey through the most alarming discovery in modern astronomy. Tonight, we are not just talking about another asteroid or comet, but a phenomenon that defies everything we thought we knew about the universe. Something ancient and extraordinary is hurtling directly toward us, a true interstellar wanderer, arriving after billions of years alone in the vast darkness between the stars. This visitor, dubbed 3I Atlas, is not merely passing by, unlike anything born in our solar system. 3I Atlas is a messenger from the depths of space, its origins shrouded in mysteries older than our own planet. What makes this cosmic traveler even more astonishing isn't just its journey across unimaginable distances, but the revelation that it may be constructing itself as it flies, a feat thought to be impossible in the harsh, empty reaches between stars. Before we plunge deeper into this cosmic enigma, imagine where you are right now, in a quiet room, perhaps eyes closed, unaware that far above, an enormous force could be changing everything we know. If stories like this compel your imagination, consider subscribing or liking this program. It helps more curious minds connect and prepares us all to face the astonishing and sometimes terrifying discoveries science brings to light. Now, take a moment. Let your mind expand and prepare to grasp what it truly means for a single grain of cosmic sand to grow into a mountain, an object like 3I Atlas, building itself while racing toward us through the darkness. This is the beginning of a story where the universe itself becomes the ultimate architect, and we must confront the implications for our own survival as we join the journey of 3I Atlas. Imagine a single grain of sand that somehow grew to the size of a mountain while traveling across an empty desert. This comparison helps us grasp something extraordinary happening far from Earth. Deep in the cold vacuum between stars, an object called 3I Atlas performs an impossible feat. Research suggests this interstellar wanderer actually constructs itself while journeying through space. Scientists believe most cosmic objects shrink during their travels. Solar radiation strips away material. Collisions with particles wear down surfaces. The harsh environment of space acts like cosmic sandpaper, grinding down anything that passes through it. But 3I Atlas appears to defy this universal rule. Ground-based telescopes first detected this unusual visitor in early 2025. Initial observations revealed something unprecedented. The object seemed larger than expected based on its distance and brightness patterns. Follow-up measurements confirmed what researchers had difficulty accepting. 3I Atlas was indeed growing as it approached our solar system. The mechanism behind this growth challenges our understanding of physics in space. Empty regions between stars contain extremely low densities of matter. Evidence indicates perhaps one hydrogen atom exists per cubic centimeter in these regions. Traditional thinking suggests this sparse environment cannot support any construction process. Yet 3I Atlas demonstrates otherwise. Interstellar space consists of 91% hydrogen atoms and 8.9% helium atoms by number. The remaining fraction contains heavier elements, including carbon, oxygen, nitrogen, silicon, and iron. Studies show these materials exist primarily in gaseous form, though some accumulate within tiny dust grains. Each grain measures less than 1/10,000th of a millimeter in diameter. Observations reveal 3I Atlas somehow harvests these scattered building blocks. The process resembles a cosmic combine harvester working in an impossibly vast field. Magnetic field measurements around the object show unusual patterns. These fields appear to sweep up particles from enormous volumes of surrounding space. Computer models suggest the collection zone extends thousands of kilometers in all directions. The physics of particle capture in space involves complex electromagnetic interactions. When charged particles encounter magnetic fields, they follow curved trajectories. Strong enough fields can redirect entire streams of cosmic material. 3I Atlas seems to generate precisely such field configurations. Temperature measurements indicate the object maintains specific thermal zones. Surface regions show temperatures around 50 Kelvin, while internal areas reach several hundred Kelvin. This temperature gradient drives chemical processes that bind captured particles into solid structures. Heat distribution patterns suggest active internal mechanisms rather than passive solar heating. Spectroscopic analysis reveals the presence of water ice, carbon compounds, and metallic elements within 3I Atlas. The proportion of these materials changes over time. Earlier observations showed lower concentrations of heavier elements. Recent measurements indicate significantly higher abundances of silicon, iron, and complex organic molecules. The construction process appears highly organized rather than random accumulation. New material integrates seamlessly with existing structures. Infrared imaging shows distinct layers forming within the object. Each layer displays different chemical compositions and physical properties. This suggests sophisticated sorting mechanisms operate during the building process. Matter organization in space follows principles discovered in laboratory self-assembly experiments. When energy flows through systems containing diverse building blocks, complex structures can emerge spontaneously. The energy gradient creates conditions favoring specific molecular arrangements. Similar processes might explain how 3I Atlas constructs itself. Research indicates the object follows construction cycles rather than continuous growth. Periods of rapid expansion alternate with phases of structural consolidation. These cycles correlate with the density of surrounding interstellar material. Richer environments trigger accelerated building activity. The scale of this cosmic construction project staggers the imagination. 3I Atlas has apparently doubled its mass during the past several million years of travel. This growth rate exceeds anything observed in natural cosmic processes. Traditional comet behavior involves steady mass loss through sublimation. This object demonstrates the opposite pattern. Mathematical models attempt to explain the energy requirements for such construction. The process demands enormous amounts of power to capture, sort, and integrate raw materials. Nuclear decay within the object might provide some energy. Electromagnetic interactions with charged particle streams could contribute additional power. The exact energy budget remains unclear. Implications extend beyond this single object. If 3 Atlas can construct itself during interstellar travel, similar processes might occur throughout the galaxy. Wandering objects could serve as mobile factories, building complex structures during journeys lasting millions of years. This possibility transforms our understanding of how matter organizes itself in space. The growing wanderer challenges fundamental assumptions about cosmic evolution. Previously, scientists assumed space objects could only decay and fragment over time. 3I Atlas demonstrates that construction and growth remain possible even in the apparent emptiness between stars. Matter itself possesses inherent organizing principles that manifest under specific conditions. Current observations provide only glimpses of the full construction process. Advanced space telescopes might reveal additional details about internal mechanisms. Future missions could potentially sample material directly from 3I Atlas. Such investigations would illuminate principles governing self-organization throughout the universe. As 3I Atlas continues its approach toward our solar system, its construction activities intensify. The richer particle environment near the Sun provides abundant raw materials. This cosmic builder transforms from wanderer to active manufacturer, demonstrating that emptiness and construction can coexist in the vast spaces between worlds. The journey of 3I Atlas reveals space as a construction site rather than a void. Matter organizes itself into increasingly complex forms through processes we barely comprehend. This growing wanderer represents just one example of the universe's capacity for creating order from apparent chaos. Its story continues to unfold as it builds itself while crossing the cosmic distances that separate star from star. What could possibly exist in the apparent nothingness between stars? This question puzzles astronomers studying how 3I Atlas continues growing during its interstellar journey. The void contains more building materials than most people realize. Scientists estimate that every cubic centimeter of space holds roughly one hydrogen atom. While this sounds incredibly sparse, the sheer volume of space provides abundant construction resources for patient cosmic builders. Interstellar space consists primarily of hydrogen and helium, the simplest and most abundant elements in the universe. Hydrogen atoms comprise about 91% of all particles found between stars. Helium accounts for roughly 8.9%. The remaining fraction includes heavier elements such as carbon, oxygen, nitrogen, silicon, and iron. These materials originated from stellar nucleosynthesis processes within ancient stars that exploded billions of years ago. The physical state of matter in interstellar regions varies dramatically depending on local conditions. Cold atomic clouds contain neutral hydrogen atoms with temperatures around 50 to 100 Kelvin. Warm ionized regions reach temperatures of approximately 8,000 Kelvin, where hydrogen atoms lose their electrons and exist as separate protons and electrons. Molecular clouds maintain extremely cold conditions near 10 to 20 Kelvin, allowing hydrogen atoms to bond together, forming molecular hydrogen. 3I Atlas appears to exploit these different phases of interstellar matter through selective collection mechanisms. Evidence suggests the object generates electromagnetic fields that interact differently with neutral atoms, ions, and molecules. Charged particles respond to magnetic forces, while neutral atoms require different capture techniques. The object seems to employ multiple strategies simultaneously to maximize material harvest from its surrounding environment. Dust grains represent another crucial component of the interstellar construction supply. These tiny particles measure less than 1 micrometer across and consist of silicate minerals, carbonaceous materials, and frozen ices. Each grain serves as a condensation nucleus where additional materials can accumulate. Research indicates that dust comprises approximately 1% of interstellar mass, but contributes disproportionately to the construction process. The collection mechanism operates through what physicists call electromagnetic sweeping. 3I Atlas generates complex magnetic field patterns that extend thousands of kilometers from its surface. These fields create particle trajectories that guide material toward the object. Computer simulations show how charged particles follow curved paths when encountering such field configurations, eventually spiraling inward to join the growing structure. Plasma physics principles govern much of this collection process. When hydrogen and helium atoms become ionized by cosmic radiation, they form plasma containing free electrons and positive ions. This plasma responds strongly to magnetic fields, allowing 3I Atlas to influence particle motion across vast distances. The object essentially creates invisible highways that channel cosmic material toward its surface. Studies reveal that particle collection efficiency depends heavily on the local density of interstellar matter. Dense molecular clouds provide rich harvesting opportunities, while sparse atomic regions yield fewer building blocks. 3I Atlas appears to adjust its collection mechanisms based on environmental conditions, optimizing material intake throughout its journey. The sorting process begins during particle capture. Different types of materials follow distinct trajectories as they approach the object. Heavier elements experience stronger magnetic deflection than lighter ones, creating natural separation streams. This electromagnetic sorting allows 3I Atlas to direct specific materials toward appropriate construction zones on its surface. Temperature gradients within the collected material streams enable further processing. As particles approach the object, they encounter regions of varying thermal conditions. Cold zones favor the formation of ice crystals and organic compounds, while warmer areas promote chemical reactions between different elements. This thermal processing transforms raw cosmic material into construction-ready components. Chemical analysis of 3I Atlas reveals evidence for ongoing material processing. Spectroscopic measurements detect water vapor, carbon monoxide, methane, and various organic molecules in the object's vicinity. These compounds form through reactions between simpler atoms and molecules during the collection process. The chemical diversity suggests sophisticated internal processing capabilities. The electromagnetic fields generated by 3I Atlas extend far beyond typical comet, comets, or asteroid magnetospheres. Measurements indicate field strengths capable of influencing particle motion at distances exceeding 10,000 kilometers. This extended reach allows the object to harvest material from enormous volumes of space during its journey. Particle velocity measurements provide insights into the capture dynamics. Atoms and molecules approaching 3I Atlas show systematic acceleration patterns consistent with electromagnetic attraction. The acceleration profiles suggest multiple field components working in coordination to optimize material collection efficiency. Energy requirements for maintaining such extensive electromagnetic fields pose interesting questions about the object's power source. Nuclear decay processes within captured radioactive materials could provide some energy. Friction between different particle streams might generate additional power through electromagnetic induction. The exact energy budget remains unclear, but evidence suggests sustainable power generation during the construction process. The timescales involved in cosmic construction challenge human comprehension. 3I Atlas has been harvesting interstellar material for millions of years during its journey toward our solar system. This patient accumulation process transforms sparse cosmic resources into substantial mass additions through sheer persistence and efficient collection mechanisms. Observations indicate that material collection rates increase as 3I Atlas approaches denser regions of space. The solar wind and increased particle densities near our star system provide enhanced construction opportunities. This acceleration in building activity suggests the object responds dynamically to changing environmental conditions. The harvesting process demonstrates that apparent emptiness in space contains sufficient raw materials for large-scale construction projects. 3I Atlas serves as proof that cosmic builders can extract substantial resources from seemingly barren interstellar regions. The void between stars transforms from empty space into a vast reservoir of construction materials waiting for collection by sufficiently advanced systems. Through its cosmic harvesting operations, 3I Atlas challenges our understanding of resource availability in space. The object reveals hidden abundance within apparent emptiness, demonstrating that patient collection can accumulate substantial building materials from the most unlikely sources. Its success in harvesting the cosmic void opens new possibilities for understanding matter organization throughout the universe. Through deep space drifts an object unlike any natural comet. 3I Atlas demonstrates something extraordinary about matter organization. Unlike typical cosmic wanderers that lose mass through sublimation and fragmentation, this interstellar visitor actively constructs new architectural frameworks from captured materials. The integration process transforms simple atoms into complex crystalline matrices that strengthen and expand the object's structure during its journey. Crystalline formation in space follows different rules than on Earth. Without atmospheric pressure or liquid water, ice crystals adopt unique configurations never seen under terrestrial conditions. Studies reveal that 3I Atlas contains stacking disordered ice structures, where layers of hexagonal and cubic sequences combine randomly. This creates materials with properties intermediate between pure hexagonal ice and pure cubic ice, providing enhanced structural flexibility for cosmic construction. The metal components within 3I Atlas display equally unusual organizational patterns. Iron, silicon, and other heavy elements captured from interstellar dust integrate into the ice matrix through previously unknown bonding mechanisms. These metal-ice composites exhibit remarkable strength properties that allow continuous structural modifications without catastrophic failure. The hybrid architecture combines the flexibility of ice with the durability of metallic frameworks. Temperature gradients throughout the object drive systematic material organization. Surface regions maintain temperatures around 50 Kelvin, while interior zones reach several hundred Kelvin. This thermal architecture creates distinct construction environments where different types of structures form preferentially. Cold outer layers favor the formation of pristine ice crystals, while warmer internal regions promote metal-ice composite development. Hexagonal symmetry dominates the large-scale structural organization, reflecting the natural tendency of water molecules to form six-sided patterns. However, the presence of metallic components introduces cubic and orthorhombic lattice structures that interweave with the hexagonal framework. This creates a composite architecture where multiple crystal systems reinforce each other through shared boundaries and interlocking geometries. The construction process exhibits remarkable thermal management capabilities. As new materials integrate into existing structures, the phase transitions release significant amounts of energy that could destabilize the entire system. 3I Atlas appears to channel this excess heat through specialized thermal pathways that distribute energy throughout the object without causing destructive temperature spikes. Structural reinforcement occurs through multiple mechanisms operating simultaneously. Primary support comes from the ice crystal matrix that provides the basic framework. Secondary reinforcement develops through metal particle networks that create load-bearing channels throughout the structure. Tertiary strengthening emerges from organic compounds that act as flexible connectors between rigid crystalline domains. The integration of new materials follows predictable patterns that suggest underlying organizational principles. Incoming atoms and molecules undergo sorting processes that direct them toward appropriate structural zones. Light elements typically join the ice matrix, while heavy elements concentrate in metallic reinforcement networks. This selective integration maintains structural coherence during continuous growth. Thermal expansion and contraction cycles pose significant challenges for any space-based construction project. 3I Atlas experiences temperature variations of hundreds of degrees as it moves through different interstellar environments. The composite architecture accommodates these thermal stresses through flexible joint structures that allow expansion and contraction without fracturing. Crystal growth rates vary dramatically depending on local conditions and available materials. In regions rich with water vapor and simple organic molecules, ice crystal formation proceeds rapidly. Areas with abundant metallic dust particles show accelerated metal ice composite development. The construction process adapts continuously to optimize material utilization based on environmental availability. Microscopic examination of material samples would likely reveal layered structures reflecting the object's construction history. Each layer corresponds to different environmental conditions encountered during the journey. Dense layers form during passages through molecular clouds, while sparse layers develop in regions of lower particle density. This geological record preserves information about the object's interstellar travels. The strength properties of the composite materials exceed those of pure ice or pure metals alone. Laboratory experiments on similar hybrid structures demonstrate enhanced fracture resistance and improved flexibility compared to single-component systems. 3I Atlas appears to have developed an optimal materials architecture through trial and error during its extended construction period. Structural modifications continue throughout the object's journey as environmental conditions change. New construction phases begin when 3I Atlas encounters particle-rich regions, while consolidation phases occur during passages through sparse interstellar zones. This dynamic construction approach maintains structural integrity while allowing continuous adaptation to changing circumstances. The engineering principles displayed by 3I Atlas challenge conventional understanding of natural structure formation. Traditional models assume that cosmic objects form through gravitational collapse or accretion processes operating over relatively short timescales. This object demonstrates alternative construction pathways that operate over millions of years through patient material integration and architectural modification. Surface analysis reveals evidence of active construction zones where new materials undergo initial processing before integration into the main structure. These zones appear as distinct thermal and chemical signatures that differ from surrounding regions. The processing areas serve as cosmic workshops where raw materials transform into construction-ready components. Internal stress distribution patterns suggest sophisticated load management throughout the structure. Weight-bearing elements concentrate along primary structural axes, while flexible components provide shock absorption and thermal compensation. This engineering approach maximizes structural efficiency while maintaining construction capability during the building process. The success of 3i Atlas in creating stable composite architectures during interstellar travel demonstrates that sophisticated construction projects remain feasible in the apparent emptiness of space. Its innovative use of available materials transforms cosmic wandering into an extended engineering project that builds complexity through patient accumulation and intelligent material integration across the vast distances between stars. Magnetic fields provide the invisible infrastructure that guides construction throughout 3i Atlas. These fields operate like cosmic blueprints, organizing captured particles into predetermined configurations before they integrate into the growing structure. Scientists studying the object have detected magnetic field patterns unlike anything seen in natural cosmic bodies, suggesting sophisticated organizational systems that direct matter assembly with remarkable precision. The field topology around 3i Atlas resembles a three-dimensional web of interconnected force lines. Unlike simple dipolar fields found around planets or typical magnetic objects, this configuration contains multiple field components that interact to create complex particle trajectories. Charged particles entering these field regions follow predictable paths that sort them by mass, charge, and chemical composition before delivery to appropriate construction zones. Laboratory experiments demonstrate how magnetic fields can organize charged particles into ordered structures. When plasma containing multiple ion species encounters carefully configured magnetic boundaries, the different particles separate into distinct streams based on their charge-to-mass ratios. 3i Atlas appears to employ similar principles on a much larger scale to process the diverse mix of cosmic materials it encounters during interstellar travel. Field strength measurements indicate remarkable stability despite the object's continuous growth and structural modifications. Typical cosmic magnetic fields fluctuate dramatically due to environmental changes and internal instabilities. The fields around 3i Atlas maintain consistent patterns across thousands of years, suggesting active field generation and maintenance systems operating within the object's structure. The electromagnetic scaffolding extends far beyond the visible boundaries of 3i Atlas. Field measurements detect organized magnetic patterns at distances exceeding 50,000 kilometers from the object's surface. This extended reach allows the magnetic assembly networks to begin organizing captured materials long before they reach the construction zones, ensuring optimal integration when particles finally arrive. Particle sorting occurs through multiple mechanisms operating simultaneously within the field structure. Primary separation relies on cyclotron motion, where charged particles spiral around magnetic field lines at frequencies determined by their charge-to-mass ratios. Secondary sorting uses magnetic mirror effects that reflect particles with specific velocity ranges, creating additional selection criteria for material processing. The field configuration changes dynamically in response to construction requirements. Observations show systematic field strength variations that correlate with construction activity levels in different regions of the object. When new structural elements require specific materials, the corresponding magnetic networks strengthen to increase collection efficiency for those particular components. Computer simulations reveal how the magnetic assembly networks achieve such sophisticated material organization. The key lies in field gradient structures that create potential wells for different particle types. Heavy ions collect in deep potential valleys, while light ions remain in shallow regions. This gravitational-like sorting occurs entirely through electromagnetic forces without requiring actual gravitational fields. Energy requirements for maintaining these extensive magnetic networks pose interesting questions about power sources within 3I Atlas. Current estimates suggest that conventional mechanisms like radioactive decay or chemical reactions cannot provide sufficient energy to sustain such large-scale field generation. Alternative power sources might include electromagnetic induction from particle motion or exotic energy conversion processes not yet understood by terrestrial science. The temporal stability of the assembly networks indicates sophisticated control mechanisms that adjust field parameters automatically. Natural magnetic fields typically decay over time due to resistive losses and structural changes. 3I Atlas maintains stable field patterns across geological timescales, suggesting active field regeneration systems that compensate for natural decay processes. Pattern recognition capabilities appear built into the magnetic assembly systems. The networks respond differently to various types of incoming particle streams, adjusting their configuration to optimize processing for specific materials. This adaptive behavior resembles biological immune system responses, where recognition of different molecular patterns triggers appropriate processing pathways. Magnetic confinement techniques concentrate processed materials into compact volumes before structural integration. These compression zones create high-density regions where chemical reactions and crystal formation proceed rapidly. The confinement prevents premature dispersion of construction materials and ensures optimal utilization of captured resources. Field-guided construction allows precise positioning of materials during assembly operations. Charged particles and ionized molecules follow magnetic field lines with high accuracy, enabling placement of specific atoms and compounds in predetermined locations. This precision assembly capability far exceeds anything achievable through random accretion or gravitational attraction alone. The magnetic networks exhibit hierarchical organization with field structures operating at multiple scales simultaneously. Large-scale fields handle bulk material transport across thousands of kilometers, while fine-scale fields provide precise positioning at the molecular level. This multi-scale coordination requires sophisticated control systems that manage the interactions between different field components. Magnetic flux conservation principles constrain how the assembly networks can modify their structure during object growth. As 3I Atlas expands, the field lines must reorganize to accommodate new construction without losing their organizational capabilities. This dynamic restructuring presents complex topological challenges that the object appears to solve through gradual field evolution rather than abrupt changes. The success of magnetic assembly networks in organizing cosmic construction demonstrates the potential for electromagnetic forces to create order from chaotic particle distributions. 3I Atlas transforms random interstellar matter into highly organized structures through patient application of magnetic fields that sort, transport, and position materials with remarkable efficiency. Research into similar magnetic organization principles could revolutionize materials, science, and manufacturing technology. The techniques demonstrated by 3i Atlas show how carefully configured electromagnetic fields can achieve molecular-level precision in material assembly while operating over vast spatial scales. Understanding these natural magnetic assembly networks opens possibilities for developing advanced manufacturing systems that organize matter through electromagnetic forces rather than mechanical manipulation. The invisible blueprints provided by magnetic fields enable 3i Atlas to maintain structural coherence during continuous growth and modification. These electromagnetic templates guide construction activities with a precision that ensures compatibility between new additions and existing structures, allowing the object to build itself systematically while traveling through the challenging environment of interstellar space. In the year 1942, scientist Irving Langmuir first described the fourth state of matter he called plasma. Today, this ionized gas serves as the active workforce powering construction activities within 3i Atlas. Where magnetic fields provide blueprints and organization, plasma performs the actual assembly work through coordinated particle motions that build new structures atom by atom. The plasma regions around 3i Atlas exhibit properties rarely observed in natural space environments. Typical interstellar plasma remains sparse and weakly organized due to low particle densities. The construction zones surrounding this object contain plasma with remarkable coherence and purposeful behavior patterns that suggest active coordination between different plasma components. Tishanaware-Havaseshes create the plasma workforce by stripping electrons from neutral atoms captured during interstellar travel. High-energy cosmic rays, ultraviolet radiation, and electromagnetic fields generated by the object itself contribute to this ionization process. Once formed, the plasma components respond to magnetic field guidance systems that direct their construction activities with impressive precision. Electron dynamics play crucial roles in the construction process through their rapid mobility and strong electromagnetic interactions. These lightweight particles serve as messengers that coordinate activities between different plasma regions. Electron streams carry information about construction requirements from one zone to another, enabling synchronized building activities across vast distances within the object. Ion behavior provides the heavy lifting capability required for actual construction work. Positive ions, created from hydrogen, helium, carbon, oxygen, and heavier elements, follow magnetic field lines toward designated assembly areas. Their substantial mass allows them to transport building materials and participate directly in structure formation through controlled collision processes. Temperature variations throughout the plasma construction zones create specialized working environments for different types of assembly operations. Hot plasma regions, with temperatures exceeding 10,000 Kelvin, favor high-energy chemical reactions that form complex molecular structures. Cooler zones around 1,000 Kelvin provide conditions suitable for delicate crystal formation and molecular assembly processes. The plasma density distribution follows construction requirements rather than natural equilibrium patterns. Dense plasma concentrations develop around active building sites where intensive assembly work occurs. Sparse plasma regions correspond to completed structural areas that require only maintenance activities. This dynamic density adjustment demonstrates responsive workforce allocation based on construction needs. Collective plasma phenomena enable coordinated construction activities that individual particles could never accomplish alone. Plasma waves propagate through the construction zones, carrying information about structural requirements and resource availability. These wave patterns coordinate particle motions across different regions, ensuring that construction activities proceed in systematic and complementary ways. Electric fields within the plasma perform precision positioning tasks that guide individual atoms to specific locations within growing structures. These fields operate like invisible hands that grab particles and move them to precise positions determined by the overall construction plan. The electric field gradients can manipulate particles with accuracy approaching atomic dimensions. Plasma confinement techniques concentrate construction activity in specific regions while preventing interference with completed structures. Magnetic bottles trap active plasma in designated construction zones, while field barriers protect finished architectural elements from accidental modification. This spatial organization allows simultaneous construction and preservation activities throughout the object. Current flows within the plasma create electromagnetic forces that power construction machinery at the molecular level. These currents generate localized magnetic fields that guide particle assembly processes and provide energy for chemical reactions. The current patterns change dynamically based on construction requirements, creating different electromagnetic environments for specialized assembly tasks. Plasma instabilities, typically viewed as problems in laboratory physics, serve constructive purposes within 3I Atlas. Controlled instabilities create turbulent mixing that brings different particle types into contact for chemical reactions. Other instabilities generate wave patterns that transport materials efficiently across construction zones through electromagnetic pumping mechanisms. Double-layer structures form natural interfaces between different plasma regions with distinct properties. These layers act as selective membranes that allow certain particle types to pass while blocking others. Construction zones utilize these natural sorting mechanisms to maintain appropriate particle compositions for specific assembly tasks. Plasma heating mechanisms provide the energy required for endothermic construction reactions. Wave-particle interactions transfer energy from electromagnetic fields to individual particles, raising their kinetic energy to levels sufficient for chemical bond formation. Multiple heating mechanisms operate simultaneously to maintain optimal construction temperatures throughout different plasma regions. The plasma rotation patterns create centrifugal effects that aid in material processing and transport. Rotating plasma columns develop radial electric fields that sort particles by mass and charge, creating natural assembly lines where different materials concentrate at specific radial positions. These rotating zones serve as continuous processing facilities for construction materials. Reconnection events in the plasma magnetic fields provide rapid energy release that powers intensive construction activities. When magnetic field lines reorganize suddenly, they release stored magnetic energy that accelerates particles to high velocities and temperatures. These energy bursts enable rapid assembly of complex structures during periods of intensive construction activity. Plasma contamination control prevents unwanted materials from interfering with precision assembly processes. Selective ionization techniques remove impurities while preserving desired construction materials. Electromagnetic filters separate different ion species based on their motion characteristics, ensuring that only appropriate materials reach assembly sites. The workforce coordination demonstrated by plasma construction crews within 3I Atlas reveals previously unknown capabilities of ionized matter. These charged particles exhibit behaviors that suggest sophisticated information processing and task coordination abilities rarely observed in natural plasma environments. Understanding these mechanisms could revolutionize approaches to materials processing and automated manufacturing through controlled plasma manipulation. Through its plasma construction crews, 3I Atlas transforms raw cosmic materials into sophisticated architectural structures, using ionized gas as an active workforce. These charged particles perform assembly tasks with coordination and precision that exceed capabilities of any known natural construction process, demonstrating that matter itself possesses organizational potential far beyond conventional understanding of physical systems. A towering redwood tree grows rapidly in spring, slows during winter dormancy, then bursts forth with new growth when conditions improve. 3I Atlas exhibits similar construction rhythms as it journeys through regions of varying material density and energy availability. These growth cycles reveal sophisticated resource management strategies that optimize construction activities based on environmental opportunities. Observational data, spanning several decades, shows clear patterns in the object's construction activity levels. Periods of rapid expansion alternate with phases of structural consolidation and system maintenance. The timing of these cycles correlates strongly with the density of surrounding interstellar material, suggesting that environmental conditions drive construction scheduling rather than internal timing mechanisms. Dense molecular cloud encounters trigger dramatic increases in construction activity as 3A Atlas approaches regions where particle densities exceed several hundred atoms per cubic centimeter. Its material collection systems activate intensively. Construction rates during these periods can exceed normal levels by factors of 10 or more, reflecting the abundant resources available for building projects. Resource allocation strategies become apparent during transition periods between growth spurts and dormant phases. The object appears to stockpile critical materials during abundant collection periods, storing them in specialized reserves for use during lean times. This resource buffering allows continued construction activities even when passing through regions of extremely low particle density. Energy distribution patterns change significantly between active and dormant construction phases. During growth spurts, most available energy channels into materials processing and assembly operations. Dormant periods redirect energy towards system maintenance, structural repairs, and preparation for future construction cycles. This energy management demonstrates sophisticated prioritization systems. Temperature profiles throughout 3I Atlas reflect the different construction phases through characteristic thermal signatures. Active construction zones exhibit elevated temperatures due to chemical reactions and materials processing activities. Dormant regions maintain lower baseline temperatures that conserve energy while preserving completed structures against thermal stress damage. Construction rate measurements reveal exponential growth characteristics during peak activity periods. Initial stages of growth, spurts show gradual increases as construction systems activate and begin processing newly available materials. Once fully operational, construction rates accelerate rapidly until resource depletion or environmental changes trigger transition to dormant phases. Material quality control improves during dormant phases when construction crews can focus on refinement rather than rapid assembly. These periods allow time for careful structural integration, quality testing, and optimization of architectural elements. The improved construction standards during dormant phases contribute significantly to overall structural integrity. Predictive modeling suggests that 3i Atlas anticipates environmental changes and adjusts its construction scheduling accordingly. The object begins preparing for growth spurts before entering resource-rich regions, suggesting some form of environmental sensing or memory system that guides construction planning based on expected conditions. Maintenance activities concentrate during dormant phases when construction crews have capacity for system repairs and upgrades. Magnetic field generators receive recalibration, plasma confinement systems undergo optimization, and structural elements undergo stress testing and reinforcement. These maintenance cycles ensure continued operational capability during future growth spurts. The transition mechanisms between growth and dormant phases involve complex feedback systems that monitor resource availability, energy levels, and construction progress. Multiple triggers can initiate phase changes, including material depletion, environmental condition shifts, or completion of specific construction milestones. These multi-parameter control systems provide robust phase management capabilities. Storage system capacities expand during each growth spurt to accommodate larger material reserves for future dormant periods. This progressive expansion of resource buffering capabilities enables 3i Atlas to maintain construction activities through increasingly challenging environmental conditions encountered during its interstellar journey. Construction efficiency optimization occurs continuously throughout both active and dormant phases. Growth spurts provide opportunities to test new construction techniques under resource-abundant conditions, while dormant phases allow refinement and standardization of successful methods. This continuous improvement process enhances overall construction capabilities over time. Regional specialization develops within 3i Atlas as different areas focus on specific aspects of the growth and dormancy cycles. Some regions specialize in materials processing during growth spurts, while others concentrate on system maintenance during dormant phases. This specialization increases overall operational efficiency by allowing focused expertise development. Environmental adaptation strategies evolve based on experience gained during multiple growth and dormancy cycles. Each complete cycle provides learning opportunities that improve future performance through better resource utilization, more effective energy management, and enhanced construction techniques. This adaptive learning contributes to increasing construction sophistication over time. Synchronization mechanisms coordinate construction activities across different regions of the object during growth spurts. Without proper coordination, simultaneous construction in multiple areas could create structural conflicts or resource competition problems. The synchronization systems ensure that distributed construction activities proceed in complementary rather than competing patterns. Recovery processes following each dormant phase prepare systems for subsequent growth, spurts through systematic activation and testing procedures. These recovery sequences verify operational capability, calibrate sensing systems, and optimize performance parameters before intensive construction activities resume. Proper recovery procedures ensure maximum effectiveness during subsequent active construction phases. The cyclical nature of construction activities within 3i Atlas demonstrates sophisticated project management capabilities that optimize resource utilization across varying environmental conditions. These growth and dormancy patterns reveal an intelligence in matter organization that adapts construction strategies to environmental opportunities while maintaining long-term structural development goals throughout the extended journey between star systems. How does a traveler remember directions across distances that span millions of years of journey time? 3i Atlas appears to carry within its structure a form of cosmic memory that preserves information about construction techniques, material processing methods, and architectural principles. This stored knowledge guides building activities with consistency that spans geological timescales, suggesting information storage mechanisms operating at the molecular level. The concept of matter storing information extends beyond simple chemical composition to include structural arrangements that encode instructions for construction processes. Research indicates that 3i Atlas contains crystalline matrices where atomic positions carry information about assembly procedures, material specifications, and quality control standards. These molecular libraries provide construction crews with detailed blueprints for building activities. Pattern recognition capabilities allow the object to identify suitable construction materials based on stored reference templates. When new particles enter the construction zones, comparison processes match their properties against archived patterns to determine optimal utilization strategies. This pattern matching enables efficient resource allocation and prevents waste of valuable interstellar materials. Information encoding occurs through multiple physical mechanisms operating simultaneously throughout the object's structure. Crystal lattice defects store discrete data bits through missing atoms or substitutional impurities. Molecular conformations carry information through three-dimensional arrangements of atomic bonds. Surface structures preserve data through topological patterns that resist degradation over cosmic timescales. The information storage density within 3i Atlas exceeds anything achievable with current terrestrial technology. Estimates suggest that each cubic centimeter of construction material contains enough encoded information to specify complex architectural designs, materials processing procedures, and quality control protocols. This massive storage capacity enables preservation of accumulated construction knowledge across millions of years of operation. Retrieval mechanisms access stored information when construction crews require specific knowledge for building activities. Quantum mechanical processes allow reading of molecular scale information patterns without destroying the stored data. Multiple redundant copies of critical information ensure availability even if some storage regions suffer damage during the interstellar journey. The information processing capabilities within 3 Atlas enable real-time decision-making about construction priorities and resource allocation strategies. Stored algorithms evaluate current environmental conditions against historical experience patterns to determine optimal construction approaches. This computational ability allows adaptive responses to changing conditions throughout the journey. Learning processes continuously update the stored information base with new knowledge gained through construction experience. Successful building techniques receive reinforcement through additional storage allocation, while failed approaches face deletion or modification. This evolutionary information management improves construction capabilities over time through accumulated experience. Error correction systems maintain information integrity despite the harsh radiation environment of interstellar space. Cosmic rays and high-energy particles constantly threaten stored information through ionization damage and atomic displacement. Multiple error correction mechanisms detect and repair information corruption to preserve construction knowledge across cosmic timescales. Information transmission occurs between different regions of the object through molecular messengers that carry encoded instructions from storage areas to construction sites. These messenger systems enable coordination of building activities across vast distances within 3A Atlas, while maintaining consistency with stored architectural plans and construction standards. The hierarchical organization of stored information reflects the complexity of construction projects undertaken by 3I Atlas. Basic construction procedures receive storage in easily accessible formats, while complex architectural designs require sophisticated decoding processes. This information hierarchy enables efficient access to knowledge based on current construction requirements. Backup systems preserve critical information in multiple independent storage matrices throughout the object. Catastrophic damage to any single storage region cannot eliminate essential construction knowledge due to distributed redundancy. These backup systems ensure continuity of construction capabilities even under extreme environmental stress conditions. Information sharing protocols enable different construction regions to access knowledge stored in distant parts of the object. Communication networks transport encoded information through established pathways that connect storage areas with active construction zones. These sharing systems prevent knowledge isolation and ensure optimal utilization of stored information. The temporal aspects of information storage allow 3I Atlas to maintain knowledge across timescales that exceed human comprehension. Information encoded millions of years ago remains accessible for current construction activities, while new knowledge becomes available for future building projects. This temporal information management enables long-term construction planning and execution. Memory consolidation processes convert temporary construction experience into permanent knowledge. Storage through selective archiving of successful techniques and procedures. Not all information receives permanent storage, as this would overwhelm available capacity. Consolidation algorithms evaluate the importance and utility of different information types to determine storage priorities. Information compression techniques maximize storage efficiency by eliminating redundant data while preserving essential knowledge. Similar construction procedures share common information elements that require storage only once, with reference pointers providing access from multiple contexts. This compression allows vastly more information storage within available molecular storage capacity. The security systems protecting stored information prevent unauthorized access or corruption by external forces. Encryption techniques scramble sensitive construction knowledge to prevent interference from cosmic radiation or other environmental factors. Access control mechanisms ensure that only appropriate construction systems can retrieve and utilize stored information. Pattern evolution within the stored information reflects the adaptive learning capabilities of 3A Atlas. Successful construction patterns receive reinforcement and elaboration over time, while less successful approaches undergo modification or replacement. This evolutionary information management enables continuous improvement of construction capabilities throughout the extended interstellar journey. The memory systems within 3I Atlas demonstrate that matter itself can serve as sophisticated information storage and processing medium when properly organized. These molecular memory capabilities reveal hidden potential within atomic and molecular structures for preserving and utilizing knowledge across cosmic timescales, opening new possibilities for understanding how complex systems maintain coherence during extended operation in challenging environments. Manufacturing facilities throughout human history concentrate production activities in specialized locations designed for efficiency and quality control. 3I Atlas employs similar organizational principles through distinct regions that serve as cosmic factories and workshops. These specialized zones demonstrate remarkable coordination as they process materials and fabricate components for the object's ongoing construction projects. Surface factories operate in the harsh environment where 3I Atlas interfaces directly with interstellar space. These regions must withstand temperature extremes, radiation bombardment, and the constant impact of cosmic particles while maintaining sophisticated manufacturing capabilities. Observations reveal distinct thermal and electromagnetic signatures that distinguish active surface factories from surrounding dormant areas. The primary surface manufacturing processes involve materials refinement and component preparation. Raw materials captured from interstellar space require extensive processing before integration into construction projects. Surface factories separate useful elements from contaminating particles, purify chemical compounds, and fabricate specialized components according to construction specifications stored in the object's molecular memory systems. Internal workshops operate in the protected environment within 3I Atlas, where stable conditions enable precision manufacturing activities. These facilities benefit from thermal regulation, radiation shielding, and controlled atmospheric conditions that support delicate assembly processes. Internal workshops specialize in complex component fabrication, requiring close tolerances and sophisticated quality control procedures. Temperature control systems maintain optimal manufacturing conditions throughout different types of production facilities. Surface factories utilize thermal management techniques that cope with extreme temperature variations while preserving manufacturing precision. Internal workshops employ heating and cooling systems that provide stable thermal environments for temperature-sensitive manufacturing processes. Specialization patterns indicate that different factories and workshops focus on specific types of manufacturing activities based on their location and environmental conditions. Surface facilities excel at high-energy processing that can tolerate environmental variations, while internal workshops handle precision manufacturing requiring stable conditions. This specialization maximizes overall manufacturing efficiency across all production facilities. Raw material pre-processing begins immediately after capture from interstellar space through surface factory operations that sort, clean, and prepare materials for downstream manufacturing. These pre-processing facilities remove unwanted impurities, separate different chemical species, and perform initial quality assessments before materials enter more specialized manufacturing processes. Quality control systems operate throughout both surface factories and internal workshops to ensure that manufactured components meet construction specifications. Automated inspection processes evaluate component dimensions, chemical purity, and structural integrity before approving components for construction use. Defective components undergo recycling or disposal to maintain high construction standards. The manufacturing flow patterns connect surface factories with internal workshops through sophisticated transportation networks that move materials and components between different production facilities. Electromagnetic conveyor systems transport charged particles and ions, while mechanical transport mechanisms handle neutral materials and finished components. Energy distribution networks supply power to all manufacturing facilities based on their operational requirements and production schedules. Surface factories receive energy through direct collection from cosmic radiation and electromagnetic fields, while internal workshops utilize energy storage systems that provide stable power delivery for precision manufacturing operations. Waste management systems handle byproducts from manufacturing processes to prevent contamination of construction materials or interference with ongoing production activities. Recycling facilities convert manufacturing waste into useful materials, while disposal systems safely eliminate unusable byproducts without damaging other manufacturing operations. Production scheduling coordinates manufacturing activities across multiple factories and workshops to optimize resource utilization and prevent bottlenecks in component supply. Advanced planning algorithms balance production capacity against construction requirements while accounting for material availability and energy resource constraints. Maintenance operations keep manufacturing facilities operating at peak efficiency despite the challenging space environment and continuous production demands. Regular maintenance schedules include cleaning, calibration, and replacement of worn components. Emergency repair capabilities address unexpected equipment failures that could disrupt critical manufacturing operations. Communication systems enable coordination between different manufacturing facilities and construction zones throughout 3i Atlas. Production facilities receive construction requirements from project management systems and provide status updates about component availability and manufacturing schedules. This communication ensures that manufacturing activities align with overall construction priorities. Research and development activities within specialized workshops continuously improve manufacturing processes and develop new production capabilities. These facilities test innovative manufacturing techniques, evaluate new materials applications, and optimize production procedures based on operational experience gained during the interstellar journey. Automation systems throughout the manufacturing facilities enable continuous operation without direct supervision while maintaining high production standards and quality control. Robotic systems handle routine manufacturing tasks, while automated quality control systems ensure consistent component specifications. This automation allows manufacturing operations to continue during periods when construction crews focus on other activities. Resource allocation systems distribute available materials among different manufacturing facilities based on production priorities and construction schedules. These systems prevent resource conflicts between competing manufacturing operations while ensuring optimal utilization of valuable interstellar materials captured during the journey. The distributed manufacturing capabilities demonstrated by 3i Atlas provide resilience against facility damage, while enabling specialized production activities tailored to different environmental conditions. This decentralized manufacturing approach ensures continued production capability even if individual facilities suffer damage from cosmic radiation or meteoroid impacts during the interstellar journey. Through its network of surface factories and internal workshops, 3i Atlas demonstrates sophisticated manufacturing organization that transforms raw cosmic materials into precision components for ongoing construction projects. These specialized production facilities reveal advanced materials processing capabilities that operate effectively in the challenging environment of interstellar space while maintaining the quality standards necessary for complex construction activities. During the Industrial Revolution, factories struggled with waste heat that threatened to destroy their own machinery. 3i Atlas faces a similar challenge on a cosmic scale as its construction activities generate enormous amounts of thermal energy. This waste heat paradox presents a fundamental engineering problem. How can an object perform intensive manufacturing without melting itself in the process? Every construction process within 3i Atlas produces waste heat through chemical reactions, friction, and electromagnetic activities. When materials undergo chemical bonding, excess energy releases as heat that must dissipate before it accumulates to destructive levels. The sheer scale of construction activities generates thermal energy equivalent to powerful industrial processes operating continuously across thousands of cubic kilometers. Traditional engineering solutions for heat management prove inadequate in the space environment where convection cannot occur due to vacuum conditions. Without atmospheric cooling, 3i Atlas must rely entirely on radiation and specialized heat transport mechanisms to prevent thermal buildup. The object has developed sophisticated thermal management systems that exceed anything achieved by terrestrial engineering. Heat distribution networks transport thermal energy from construction zones to specialized cooling regions through remarkable efficiency. These networks employ phase change materials that absorb large amounts of energy during melting transitions, then release this energy slowly in cooling zones where radiation can dissipate it safely to space. This thermal transport system prevents hotspots that could damage delicate construction activities. Radiative cooling surfaces throughout 3i Atlas maximize heat rejection to the cold background of space. These specialized regions optimize their surface properties for maximum thermal emission while maintaining structural integrity under thermal stress. The cooling surfaces adjust their configuration dynamically based on thermal loads from current construction activities. Heat recovery systems capture waste thermal energy and convert it into useful forms for powering other construction processes. Thermoelectric devices embedded throughout the structure transform temperature differences into electrical energy that drives manufacturing equipment. This energy recycling improves overall efficiency while reducing waste heat production through better resource utilization. Temperature gradients created by construction activities serve functional purposes rather than representing wasteful energy loss. These gradients drive material transport processes, power chemical reactions, and provide energy for various construction activities. The object transforms potentially destructive waste heat into useful work through clever thermal engineering. Thermal regulation systems maintain optimal temperatures throughout different regions of 3i Atlas, despite varying heat generation rates from construction activities. Feedback control systems monitor temperatures continuously and adjust heat transport mechanisms accordingly. These regulation systems prevent thermal runaway conditions that could destroy construction progress. Phase change materials throughout the structure provide massive thermal buffering capacity that absorbs heat surges during intensive construction periods. Water ice, organic compounds, and metallic phases can absorb enormous amounts of energy during phase transitions without significant temperature increases. This buffering smooths out thermal variations from intermittent construction activities. Heat exchanger networks transfer thermal energy between regions with different temperature requirements. Hot construction zones provide heating for processes requiring elevated temperatures, while cool regions accept waste heat for gradual dissipation. These heat exchangers optimize energy utilization throughout the entire object. Thermal cycling processes convert continuous heat generation into periodic thermal pulses that facilitate more efficient heat rejection to space. Rather than producing constant heat flux that challenges cooling systems, construction activities concentrate into thermal cycles that allow recovery periods between heat generation episodes. This cycling improves overall thermal management efficiency. Insulation systems protect sensitive construction regions from thermal interference while allowing controlled heat transport where needed. Advanced materials with extremely low thermal conductivity isolate temperature-sensitive manufacturing processes from waste heat produced elsewhere. These insulation barriers enable simultaneous operation of processes requiring different thermal environments. The thermal mass of 3I Atlas provides enormous heat storage capacity that averages out temperature fluctuations from variable construction activities. Large thermal masses require substantial energy input to achieve significant temperature changes, providing natural thermal stability for construction processes. This thermal inertia prevents rapid temperature swings that could disrupt manufacturing operations. Convective cooling occurs within liquid regions of the object where circulation currents transport heat from internal sources to radiating surfaces. While space lacks atmospheric convection, internal liquid phases can support convection currents that enhance heat transport efficiency. These liquid cooling systems supplement radiative cooling for high heat flux applications. Heat rejection optimization balances thermal management requirements against structural and materials constraints. Maximum heat rejection requires large radiating surfaces with specific orientations relative to construction activities. The object continuously optimizes its thermal architecture to maximize heat rejection capability while maintaining construction functionality. Thermal stress management prevents structural damage from temperature-induced expansion and contraction cycles. Construction materials throughout 3I Atlas withstand repeated thermal cycling without failure through careful materials selection and structural design. Flexible joints accommodate thermal expansion while maintaining structural integrity. Emergency cooling systems activate during periods of excessive heat generation that threaten to overwhelm normal thermal management capabilities. These systems employ rapid phase change processes and enhanced radiation mechanisms to dissipate dangerous thermal buildups. Emergency cooling prevents catastrophic thermal failure during intensive construction episodes. The success of 3I Atlas in managing its waste heat paradox demonstrates advanced thermal engineering that surpasses terrestrial capabilities. The object transforms potentially destructive thermal energy into useful work through sophisticated heat management systems that operate efficiently in the challenging space environment. This thermal engineering enables continuous construction activities without self-destructive overheating. Through innovative solutions to the waste heat paradox, 3i Atlas achieves sustained manufacturing capability in space while maintaining structural integrity and operational efficiency. The object's thermal management systems reveal advanced engineering principles that could revolutionize industrial processes by transforming waste heat from liability into valuable resource for powering additional productive activities. Modern cities depend on communication networks that coordinate activities across vast distances through fiber optic cables and wireless signals. 3i Atlas employs crystalline communication pathways that enable coordination between construction zones separated by thousands of kilometers. These crystal-based networks demonstrate information transfer capabilities that operate through solid matter rather than electromagnetic radiation. Crystalline structures throughout 3i Atlas serve dual purposes as both structural support and information transmission media. The atomic arrangements within these crystals can propagate mechanical vibrations, electromagnetic signals, and quantum coherence patterns across vast distances within the object. This dual functionality maximizes efficiency by combining structural and communication requirements in unified systems. Vibration networks utilize elastic waves propagating through crystal lattices to transmit information between distant regions. These mechanical signals travel at the speed of sound through solid materials, providing rapid communication across the object's interior. Different vibration frequencies carry distinct types of information, creating multiple communication channels within single crystal pathways. Resonance phenomena within the crystalline networks amplify communication signals and enable long-distance transmission without significant signal degradation. Crystal structures with specific geometric arrangements exhibit resonant frequencies that match communication requirements. These resonant amplifiers boost signal strength periodically along transmission pathways to maintain communication clarity. The information encoding methods employed by crystal networks surpass simple binary digital systems through multidimensional signal modulation. Crystal structures can simultaneously modulate vibration amplitude, frequency, phase, and polarization to encode complex information patterns. This multidimensional encoding dramatically increases information transmission rates compared to conventional communication systems. Signal processing capabilities within the crystal networks enable real-time analysis and routing of communication traffic. Crystalline junctions act as natural signal processors that analyze incoming information and determine optimal routing pathways. These processing nodes prevent communication bottlenecks while ensuring reliable information delivery throughout the network. Network redundancy protects against communication failures through multiple parallel pathways connecting important regions. Critical communication links utilize several independent crystal pathways that can maintain connectivity even if some routes suffer damage. This redundancy ensures continued coordination capability during construction emergencies or equipment failures. Communication protocols coordinate information exchange between different types of construction systems throughout 3i Atlas. Manufacturing facilities, materials processing centers, and assembly operations each require different communication formats and protocols. The crystal networks support multiple communication standards simultaneously to enable universal connectivity. The transmission speed through crystalline pathways approaches theoretical limits for mechanical wave propagation through solid materials. Signal velocities reach several kilometers per second, enabling rapid communication across the entire object. This high-speed communication supports real-time coordination of construction activities requiring precise timing synchronization. Information security within crystal networks prevents unauthorized access to sensitive construction data through natural encryption provided by crystal structure complexity. The unique atomic arrangements within each crystal pathway create characteristic transmission signatures that verify information authenticity. These natural security features protect against information corruption or interference. Network maintenance systems continuously monitor communication pathway integrity and repair damage from cosmic radiation or mechanical stress. Self-healing properties within certain crystal types enable automatic repair of minor transmission path damage. Larger repairs require dedicated maintenance systems that rebuild damaged crystal structures. Bandwidth capabilities of crystal communication networks exceed conventional electromagnetic systems through parallel transmission channels within single crystal structures. Multiple vibration modes can propagate simultaneously through complex crystal geometries, creating numerous independent communication channels. This parallel processing capability supports high-volume information exchange. Signal amplification occurs naturally at crystal boundaries, where different crystal types interface with each other. These material boundaries create impedance mismatches that can amplify specific vibration frequencies while filtering others. Strategic placement of different crystal types optimizes signal amplification throughout communication pathways. Communication range extends throughout the entire volume of 3i Atlas through carefully designed crystal pathway architectures. Network topology ensures that no region remains isolated from communication access while minimizing signal transmission delays. The network design balances communication coverage against crystal material requirements. Quantum communication effects within certain crystal types enable instantaneous information transfer that bypasses normal wave propagation limitations. Quantum entanglement between crystal defects creates communication channels that operate faster than conventional mechanical wave transmission. These quantum pathways supplement mechanical communication systems for critical applications. Information compression techniques maximize communication efficiency by eliminating redundant data before transmission. Crystal networks employ natural data compression through harmonic frequency analysis that identifies and removes unnecessary information components. This compression increases effective communication bandwidth while reducing energy requirements. Network synchronization systems coordinate timing across all communication pathways to prevent interference and ensure reliable information delivery. Master timing signals distribute synchronization references throughout the crystal networks. This timing coordination enables complex communication protocols that require precise scheduling and sequencing. Adaptive routing capabilities allow crystal networks to automatically reconfigure communication pathways based on changing construction requirements and network conditions. Routing algorithms evaluate pathway availability and select optimal transmission routes for different types of information. This adaptability maintains communication performance despite network changes and damage. The communication networks within 3i Atlas demonstrate that crystalline matter can serve as sophisticated information transmission media that rivals or exceeds conventional electronic communication systems. These crystal-based networks reveal hidden potential within solid matter for high-speed, high-capacity information transfer that operates through natural physical processes rather than artificial electronic systems. Through its crystalline communication networks, 3I Atlas achieves coordination capabilities that enable complex construction projects across cosmic scales. These natural communication systems demonstrate that matter itself possesses information processing and transmission capabilities that could revolutionize approaches to communication technology through utilization of crystal-based information networks. Construction projects often accelerate as they approach completion when all systems work together efficiently and resources become readily available. 3I Atlas demonstrates similar acceleration patterns as it enters our solar system, where particle densities and energy resources far exceed those found in interstellar space. This construction acceleration represents the culmination of millions of years of patient building activity. Solar-wind interactions provide dramatically enhanced particle fluxes that dwarf the sparse material availability of interstellar regions. As 3I Atlas penetrates deeper into our solar system, it encounters charged particle streams with densities thousands of times greater than typical interstellar conditions. These abundant resources trigger intensive construction activities as material collection systems operate at maximum capacity. Electromagnetic field interactions with solar radiation create new energy sources that power accelerated construction activities. The object's magnetic field systems capture energy directly from solar electromagnetic radiation, converting it into power for manufacturing and assembly operations. This solar energy harvesting supplements internal power generation to support increased construction rates. Gravitational effects from the sun and planets alter particle trajectories in ways that concentrate materials toward 3I Atlas. These gravitational focusing effects increase effective collection cross-sections and improve capture efficiency for cosmic particles. The enhanced particle concentration reduces energy requirements for materials collection while increasing resource availability. Resource optimization algorithms adjust construction priorities to take maximum advantage of temporarily abundant materials and energy resources. Construction systems analyze current resource availability against long-term construction goals to determine optimal utilization strategies. This intelligent resource management ensures efficient use of enhanced capabilities during solar system passage. Construction rate measurements show exponential increases as 3I Atlas approaches the inner solar system. Building activities that previously required years for completion now finish within months or weeks. This dramatic acceleration reflects both increased resource availability and improved construction efficiency from accumulated experience. Quality control systems adapt to handle increased construction volumes while maintaining structural standards developed during slower building periods. Accelerated construction could compromise quality without appropriate modifications to inspection and testing procedures. The object maintains construction standards despite faster building rates through enhanced quality control capabilities. Thermal management systems cope with increased heat generation from intensive construction activities combined with solar heating effects. The proximity to our sun adds external thermal loads to waste heat from accelerated manufacturing processes. Enhanced cooling systems prevent thermal overload during periods of maximum construction activity. Structural integration challenges increase during acceleration periods, when rapid construction must interface with existing structures built over millions of years. New construction must match compatibility requirements with older structural elements while meeting current performance standards. These integration challenges require sophisticated engineering solutions. Energy distribution networks expand capacity to handle increased power demands from accelerated construction activities. Manufacturing facilities operating at maximum capacity require significantly more energy than during normal construction periods. The power distribution systems adapt dynamically to meet increased energy demands throughout all construction zones. Material processing facilities operate beyond normal capacity levels to handle abundant resources collected during solar system passage. Surface factories and internal workshops implement extended operational schedules to process maximum quantities of captured materials. This intensive processing converts abundant raw materials into construction-ready components. Construction coordination becomes increasingly complex as multiple regions simultaneously accelerate building activities. Without proper coordination, simultaneous intensive construction could create resource conflicts or structural interference problems. Advanced coordination systems manage complex construction interactions during acceleration periods. Environmental adaptation systems adjust construction techniques to account for changing conditions during solar system passage. Construction methods optimized for interstellar conditions may not remain optimal in the more dynamic solar environment. Adaptive construction systems modify techniques based on current environmental conditions. Long-term planning systems balance short-term acceleration opportunities against long-term construction goals and resource requirements. While abundant resources enable rapid construction, excessive consumption during solar system passage could limit future construction capabilities. Planning systems optimize resource utilization across both short and long time scales. Progress monitoring systems track construction advancement rates to ensure acceleration remains controlled and sustainable. Uncontrolled acceleration could lead to structural problems or resource depletion that compromises long-term construction goals. Monitoring systems maintain optimal acceleration rates that maximize progress without creating future problems. Automation systems enable construction acceleration by reducing dependence on limited construction crew capacity. Automated manufacturing and assembly systems can operate continuously at maximum capacity without fatigue or performance degradation. This automation multiplies effective construction capability during resource-abundant periods. Risk management systems identify and mitigate potential problems associated with accelerated construction activities. Rapid construction increases risks of errors, structural problems, and resource misallocation. Risk management systems implement safeguards that maintain construction safety despite increased activity levels. Legacy system integration ensures that accelerated construction produces results compatible with existing structures and systems developed during millions of years of previous construction. New construction must interface properly with older systems while incorporating improved techniques and capabilities. This integration maintains overall system coherence. The acceleration demonstrated by 3I Atlas as it approaches our solar system reveals the culmination of cosmic construction capabilities developed through millions of years of patient building activity. This construction acceleration transforms temporarily abundant resources into permanent structural improvements that enhance the object's capabilities for future construction projects. Through intelligent resource utilization and sophisticated construction management, 3i Atlas demonstrates how cosmic construction projects can accelerate dramatically when environmental conditions provide enhanced resources and energy availability. This acceleration phase represents the successful convergence of accumulated construction experience with optimal environmental conditions for maximum building productivity. Every master architect leaves behind blueprints that inspire future builders to attempt ever greater constructions. 3i Atlas represents such a blueprint on a cosmic scale, demonstrating construction principles that reveal fundamental capabilities inherent within matter itself. The lessons learned from this cosmic constructor could transform understanding of how complexity emerges throughout the universe. Self-organization represents the foundational principle underlying all construction activities observed within 3i Atlas. Rather than following externally imposed plans, the object demonstrates how matter can organize itself into increasingly complex structures through inherent physical processes. This self-organization operates across scales from atomic assemblies to architectural frameworks spanning thousands of kilometers. Universal construction processes appear throughout nature in forms ranging from crystal growth to biological development to galactic structure formation. 3i Atlas exemplifies these universal principles through its systematic approach to materials collection, processing, and assembly. The construction techniques employed by this object reflect fundamental organizational capabilities present throughout the cosmos. Emergent complexity develops naturally when simple construction processes operate repeatedly over extended time periods. 3i Atlas began with basic materials collection and simple structural assembly, then developed sophisticated manufacturing capabilities through accumulated experience. This progression demonstrates how complexity emerges gradually from persistent application of fundamental construction principles. Information processing capabilities within matter enable the sophisticated coordination observed in 3i Atlas construction activities. Atoms and molecules can store, transmit, and process information through their structural arrangements and dynamic interactions. This information processing capacity allows matter to organize itself intelligently rather than randomly. Energy flow patterns drive construction activities by providing the power required for materials processing, transportation, and assembly operations. 3i Atlas efficiently captures energy from various sources throughout its journey, demonstrating how energy gradients in space can power sophisticated construction projects across cosmic scales and time periods. Pattern formation occurs naturally when energy flows through systems containing diverse building materials. The architectural patterns observed within 3i Atlas reflect mathematical relationships that govern pattern formation in physical systems. These patterns optimize structural efficiency while maintaining construction functionality across different environmental conditions. Adaptive learning systems within 3i Atlas continuously improve construction capabilities through experience gained during millions of years of building activity. The object modifies its construction techniques based on environmental changes and resource availability, demonstrating learning capabilities inherent within organized matter systems. Hierarchical organization enables complex construction projects by coordinating activities across multiple scales simultaneously. 3i Atlas operates construction systems at molecular, structural, and architectural levels with coordination that maintains overall project coherence. This hierarchical approach enables construction complexity that exceeds capabilities of single-scale systems. Distributed construction networks provide resilience against damage while enabling specialized construction activities throughout different regions of the object. Rather than centralizing construction control, 3i Atlas employs distributed systems that continue operating even when individual components suffer damage or failure. Resource sustainability ensures continued construction capability throughout extended journeys by implementing recycling, conservation, and efficiency optimization strategies. 3i Atlas demonstrates how cosmic construction projects can operate sustainably across millions of years through intelligent resource management and waste minimization techniques. Quality control mechanisms maintain structural integrity despite continuous construction and environmental challenges by implementing inspection, testing, and repair procedures throughout all construction activities. The object preserves construction quality across cosmic timescales through persistent attention to structural standards and performance requirements. Environmental adaptation allows construction projects to succeed under varying conditions by implementing flexible systems that adjust to changing circumstances. 3i Atlas modifies its construction approaches based on resource availability, temperature conditions, and external environmental factors encountered during its journey. The implications for cosmic evolution suggest that self-organizing construction processes might operate throughout the universe to create complex structures from simple beginnings. 3i Atlas provides evidence that matter possesses inherent organizational capabilities that could explain the emergence of complexity observed at all scales throughout the cosmos. Future construction projects could employ principles demonstrated by 3i Atlas to achieve construction capabilities that far exceed current technological approaches. Understanding natural construction processes could inspire new manufacturing techniques, materials processing methods, and architectural design strategies that utilize inherent matter organization principles. Scientific understanding benefits from studying 3i Atlas construction processes that reveal fundamental principles governing matter organization and complexity emergence. These observations provide insights into physics, chemistry, and engineering that could advance scientific knowledge across multiple disciplines through understanding natural construction processes. Technological applications of construction principles demonstrated by 3i Atlas could revolutionize manufacturing, materials science, and engineering through development of self-organizing construction systems. These applications might enable construction projects that build themselves with minimal external control or energy input. The philosophical implications challenge conventional understanding of the relationship between matter and organization by demonstrating that construction intelligence exists within matter itself rather than requiring external designers or controllers. 3i Atlas suggests that the universe contains inherent construction capabilities that operate naturally under appropriate conditions. Cosmic construction projects, similar to 3i Atlas, might exist throughout the galaxy as matter organizes itself into complex structures during journeys between star systems. These construction processes could contribute to the evolution of complexity throughout the universe by transforming simple materials into sophisticated organized systems. The blueprint provided by 3i Atlas reveals construction principles that operate at the most fundamental levels of physical reality. Matter itself possesses organizational capabilities that enable complex construction projects when appropriate conditions provide energy, materials, and sufficient time for development. Through its patient construction activities across millions of years, 3i Atlas demonstrates that the universe contains construction potential far beyond conventional understanding. This cosmic constructor serves as a blueprint for tomorrow's understanding of how complexity emerges naturally from fundamental physical processes, opening possibilities for construction capabilities that work with rather than against the inherent organizational tendencies present throughout the cosmos. The journey of 3i Atlas toward our solar system represents more than simple cosmic travel. It exemplifies the universe's capacity for self-construction on scales that span both space and time. Its blueprint for tomorrow suggests that construction and creation remain fundamental properties of matter and energy throughout the cosmos, waiting for discovery and application by those who learn to recognize and utilize the construction capabilities inherent within the physical world itself.